So pretty much this entire first part of the unit, all you've been doing is literally counting, right? How many ways can you do this? How many arrangements are there for this? How many ways can you select whatever? Well, all of those are like small parts of actually calculating a probability. Ultimately, what we're most interested in is the percent likelihood, which we just say, what's the chance, right, that something will happen? Just like the weatherman predicts, 90% chance of rain or whatever. Okay, that's what we're interested in. By definition, okay, and this is huge. Okay, this always baffles me. So I just want everyone to listen right now so that you never do this as a possible answer. Okay? What is the maximum amount percent chance of anything happening? 100. 100. What does that equal as a number? 1. What is the smallest percent chance? 0, which is just 0. Does that make sense? So by definition, even if it's a theoretical or an empirical probability, all probabilities are greater than or equal to 0 and less than or equal to 1. So if you ever as things get more and more complicated, students tend to lose sight of that. They'll just start remembering pieces and bits of formulas, and they'll start doing all these things with all these numbers, and then somehow they'll get a probability of 1.4. And they'll turn that in, right? If you get a probability of 1.4, what does that mean? You messed up somewhere, right? So you might as well try something else and try to get it so that it makes more sense. All right, so just remember that. Never ever should you have a probability that's greater than 1, because that's impossible. Now, theoretical, this is most of what we're going to do. So this is just based on possibilities. Possibilities. So for example, just really basic, if I have a coin and I flip the coin, it's either going to land on heads or tails. So that we would say that that's 2 theoretical outcomes, right? What is the probability that when I flip the coin I get tails? Well, you said 50-50, but let's use a fraction. What would it be? 1 out of 2, right? Because there's only one tail out of the 2 entire possibilities. Does that make sense? That's what we call theoretical probability. Empirical is just a fancier way of saying experimental. This would be like me actually sitting here with a coin, flipping it a whole bunch of times because I don't know that the probability is 1/2, and recording my results and then using that to kind of figure it out. So for example, if I flip the coin 100 times and 48 of those were tails, then I would say 48 out of 100, or 48%, is the probability of tails. Does that make sense? Based on the experiment. Theoretical, though, we know is 50. Does that make sense? Question? Yes. All right. So let's talk about theoretical probability first. Okay? The number of outcomes in event E, I like to just call this number of favorable outcomes. Oh, yeah, because Christian left, so you're going to have to wait. So the number of favorable outcomes is going to be the numerator. Okay? The total number of possible outcomes is the denominator. This is kind of the notation they use. Okay? This just means number of favorable outcomes in the events, and then this is the number of the entire possibilities. Okay? So, first example, we talked about already, tossing a coin. The sample space, what are the 2 things that could happen? I could either get heads or tails. Does that make sense? The event, there's just heads is what I'm looking at in this problem. We want the probability of a coin landing heads in a coin toss. So this is the event that I want. These are the possibilities. I know this is really basic, but does it make sense? All the terminology and all that stuff, where it's coming from. Okay. Why don't you guys try example 1b? Okay. Rolling a dice, 6 possible outcomes. Here they are. What is the probability that when you roll the dice, you get a 3? And then just try all of these. What about an even? What's the probability of that? Let's see how we do. Okay, let's go through it. What is the probability that when you roll the die, you get a 3? Does anyone not get that? Okay. What is the probability that we're going to roll an even number? 3 out of 6, which reduces to 1/2. So we always do want to reduce our fraction, so get in the habit of doing that. You guys know on the calculator how to make this into a reduced fraction, right? You press math, the first option, and then it does it automatically for you in case you don't know that 3/6 is 1/2. We should know that, but just in case, maybe when they get harder, you want to make sure you can do that, okay? A number less than 5, what's the probability of that happening? So 2/3 started as 4 out of 6. What about a number less than 10? So 1. Make sense? What about a number greater than 6? Okay. Again, this section is really basic, but it's so crucial that we're like 100% with these little ones, because eventually it's going to be, you have 23 students in a classroom, 12 are male, 11 are female. What's the probability that I choose 2 girls and 1 boy to go do an errand and go get my Kleenex boxes out of the car or something because I forgot to bring them in? That would be a more complicated calculation, but it's all based off of everything we've been doing. Okay, let's turn the page. Let's just do this on the fly, and I think we'll just get through example 3, and that'll be a good place to stop. Okay, and please be completely honest. How many of you are not familiar or are not comfortable with playing cards? Okay, so you will get, I don't have them with me now, but like for a quiz or a test, you'll actually get like a little sheet of paper that'll actually have a picture of every single card in case you forget how many there are and what the suits are, okay? But essentially there's 52 cards in a deck of cards. There are 4 different suits, okay? And there are 2 red suits, 2 black suits. What are the 2 red ones? Hearts and diamonds are the red, and then clubs and spades are the black ones. Okay, so you can write this down in case you're not familiar with it. Besides knowing that there's 4 suits, now you have to know that every card, ace, 2, 3, 4, so these are all the possible cards. It goes up to 10. And then we have a jack, a queen, and a king. I like to put the ace at the beginning so it looks like 1, 2, 3, 4, 5. But yeah, usually an ace is worth the highest. But this is all the different possible rankings. Okay, does that make sense? All right, so hopefully just with that, we should be able to answer this. Jason, what's the probability of if I pick a card, just one card, that I pick a king? How'd you get that? So 4 out of 52, and you got 1/13. You guys see how he did that? Okay. What is the probability, Andrea, that I get a heart? Not quite. How many hearts are in the whole deck? Each suit has 13 of these. So there's 13 aces, there's 13 hearts, and those 13 hearts are ace, 2, 3, 4, all the way up to king. There's 13 clubs, same thing. Does that make sense? So there are 13 possible hearts, 52 total possibilities. So you get what when you reduce this? A fourth. Okay. Andy, what about probability of just picking a red card? That is correct. What about a black queen? So we're talking queen of clubs or queen of spades. Jared.
There's 2 queens. 2, right?
Yep. Which reduces to 1/26. Very good. And the very last one, Julia, the king of spades. What's the probability that you get that one? I just told you the answer. That you get that card. Thank you. Moving on. Last example, genetics. Okay. In the interest of time, I'm just going to tell you what all this stuff is saying, so we don't spend a minute reading it. But essentially, if we have 2 parents and they have a child, this is kind of important, but each parent is either a carrier or not a carrier for the cystic fibrosis disease. Most people don't carry that gene, okay? But assuming that they do, they either have the disease or they're at least a carrier. Does that make sense? So you can have these genes hidden in you and it doesn't mean that you're carrying or that you have the disease, but you carry that gene. So if we have 2 parents, each parent has one gene that is indicative of, yes, you carry the gene. The capital C means that you don't, okay? If you end up with CC, that's a person that actually ends up having the disease. Does that make sense? If you end up with CC or capital C, little c, this is not a carrier. This is a carrier because you have that small little c, but no disease. Does that make sense? And then the only other option is you have 2 little c's, which is a carrier. You have the gene and you have the disease. Okay? So if these 2 parents have a child, what are the 4 possible outcomes? In this box, you would have 2 little c's. In this one, we have a big and a little c. Here we have the same thing, a big and a little c. Here we have 2 big c's. So what's the probability? How many outcomes are there, first of all? 4. And how many of them show us would have the cystic fibrosis gene? Just 1. Right? In order to have the disease, or I'm sorry, not the gene, but have the actual disease, I misread that. That's 2 little c's, so that's 1 out of 4. Okay? But now if I asked you, and I kind of did by accident, how many of these carry the gene? Now there would be 3. The one that has the disease, and then these 2 that are carriers but don't have it. Does that make sense? So that'd be 3 out of 4.
Yeah.
All right. Good work today. That's the end.